Anyway, again, welcome to our talk tonight. We are, folks who don't know about us, you know, we're the Peninsula Astronomical Society Club. We've been around since 1949 in the South Bay here, and we have about 140 members or so at the moment. Things that the club does primarily is we're the ones who host the public viewing sessions of the Foothill College Observatory. We do these talks on occasion. We used to do them every month. And then we got disrupted by COVID just like everybody else, so we're still kind of getting our legs back under us. So they're kind of, as you know, every 2 or 3 months at the moment. And then also we do, during the summer, we have a public viewing at Foothills Park up in Palo Alto for folks. We have Maria back here is the one who coordinates that for us. Also, I'm curious, Maria is the one who's running our meetup. I'm just wondering how many folks here are, because of the meetup that was scheduled for tonight. Good number of you, thanks, awesome. So we're also a club, so I mean, at some point we'd love it if you could join and be part of our club. You know, membership benefits include, we actually have a whole suite of telescopes, like 15 really nice telescopes that are free to loan out to club members. So if you ever want to like try out a telescope and take it home and you know, basically kick the tires, get used to it, we have a number of scopes you can choose from for that. We also actually have you know, our own private viewing site up off of Skyline. So if you're a hardcore observer, you can take your telescope up there. We also have, if you have a telescope in a dome up there, you can just go up there and use our telescope. So, and that's, you get half of a dark sky up there for, you know, you can actually see part of the Milky Way and whatnot. And then of course you get to be part of our community. A lot of people who are astronomy lovers and whatnot know about the sky, so you can be part of the group. Anyway, that's enough of my overhead stuff. I'm Gary, by the way, president of the club. I'm going to pass it off now to our Antonio, who is the one who arranges all these wonderful speakers.
So thank you, Gary. Another side benefit is we teach you how to drive the telescope, and it's a big enough one over at Foothill College. So if you want to join the club, we'll teach you how to drive the telescope, and you too can drive it. So that'd be fun. So, well, tonight I'm really excited to have Dr. Aalbers, who's world class. He's doing research on dark matter, which is a subject. This is a mystery that's been going around for almost 100 years. Those of you who know a little bit of astronomy, there's a fellow named Fritz Zwicky who's analyzing galaxy clusters, and they should have been flying apart, but they didn't. So he said, something's holding this together. Then fast forward a little bit further on, there's a famous astronomer, Vera Rubin, who analyzed the rotational speed of the galaxy and said the stars should have been flying apart, but they don't. Something's holding it together. And it's not, I mean, this something is substantial. It's even, you know, I'm not going to take all the explanations, but it's not predicted by the standard model. It's not predicted by physics as we know it. And people are analyzing it both at the astronomical level as well as down at the particle physics level. This is a real mystery. It's almost 100 years old, and so far, we don't really know what's going on. So I'm really super thrilled to have Dr. Aalbers here from Stanford, and maybe he can shed some clarity on the subject and shed a little light on this dark subject. So with all ado, no further ado, thank you so much for coming.
Thank you, Antonio, for that very generous introduction. So hi, I'm Jelle. I've been called various things like Jill or Heffe or Jelly, but it's just Jelle. I'm from the Netherlands, and I'm really glad to be here because when I was a little kid, I used to go to my local astronomy club lectures, and I got really excited by astrophysics. And I've talked about my work to like lots of like scientists and conferences, but I've never talked to an astronomy club. So I'm very glad to share this with you today, and to be talking about my favorite subject, which is dark matter. Now, dark matter is, I think, the most embarrassing open problem in physics, because it is both something that we have known for a long time, for like 50 or 100 years, we have known that something big is missing, that the matter that you see around you, that stars and planets and everything around you is made of, is not enough to explain what our universe is made of. that our universe must have some other component. We have known this for a long time, and we have many ideas about it. But despite the fact that we can describe the physics around us in minute detail, we have still to solve this very important mystery. So that's why I say it is sort of our universe's worst kept secret. We've known this about this a long time, and we're still working on how to solve this. So let me just start the timer so I don't keep you forever. So I'm planning to talk you through 3 aspects of dark matter today. First, I'm of course going to talk about what is dark matter. Then we're going to talk a little bit about why we believe that it exists. And finally, about how can we try to detect it, to try to specifically say, oh, it's that kind of dark matter, and not just any kind of dark matter. And at any point in my talk, if you have a question, feel free to raise your hand, and I'd be happy to talk with you, especially if I say something that's unclear. We'll also have some time at the end to discuss, but please feel free to just interrupt me. It's totally okay. All right. Okay, then without further ado, let's get started. What is dark matter? Well, let's start with the words dark matter. So first of all, it is some kind of matter. So it is some kind of substance with mass, right? So it's not like light that it gets energy but no mass. It's something, basically. It's denser in some places than others. It's not just some homogeneous, some uniform thing all the way around the universe. There's more of it in some places, like in a galaxy, and less of it outside the galaxy. And most importantly for today, it feels and exerts gravity like anything else. So gravity is a force that exists between any 2 massive objects, and of course the most massive objects exert it most, so that's what you feel it, and that's what you can see in astronomy. And dark matter participates in this just like any other matter. So far it looks like a pretty normal kind of substance. But now we get to the dark part. The dark part means that it cannot emit or absorb light. So we shouldn't have called it dark matter, we should have called it transparent matter. But dark matter sounds cooler, so we call it dark matter. And with all these things, I have to put in a slight, as far as we can detect, because we haven't seen it, but maybe it has a very small chance of interacting with light. That would be great, because then we can detect it much more easily. But that's not all. Not only doesn't it interact with light, it also passes through regular matter unhindered. So there could be a whole, a storm of dark matter passing through us right now, and we would never notice. So it is something that has very small interactions with everything around us. That's the way we technically phrase this in physics. We can also say that it only interacts through gravity, but not through all the other fundamental forces of the universe, right? There's electromagnetism, and there's 2 nuclear forces, and it does not seem to participate in any of those, but it does seem to do gravity. And finally, it doesn't seem to show any significant self-interactions. What I mean by that is that, sure, it clumps together because it exerts gravity and it feels gravity, but it's not like it clumps together so much that there seems to be some stronger force between the dark matter particles than gravity. Again, as far as we can detect so far. And it is certainly possible that all of these turn out to be actually, it is slightly possible to interact with light, with matter, and with itself. So that's the dark part, that's what the matter is. So that's dark matter. Now where do we find this dark matter? Well, almost everywhere. Unfortunately, we can't see it. So we have had a lot of evidence for it, and we can come back to that later, but for now I'm just going to show you the things as we believe, and then we'll get to the evidence. So this is a computer simulation of how the dark matter could look like in our local neighborhood, so around the galaxy. So you can see this weird tendril-like pattern, and you could imagine that if you had a superpower or a magic glasses that you could look at the sky and just see dark matter, you would see something like this in the sky. By the way, if you do have such a glasses, please come talk to us. We would like to get in touch with you. So now, here I'm only showing the dark matter, not any of the galaxies or the other exciting things.
What's the sort of scale of this picture?
Excellent question. I'm going to show you right now, because I can put the galaxy in this picture. That's our galaxy. Right? So our galaxy is part of this huge cloud of dark matter. We call it a halo. So it's called a dark matter halo that our galaxy lives within. And actually on the scale, I was talking to a colleague that's an expert on these computer simulations. And I showed it to him and said, do you think that the scale is roughly right? And he said, I don't know, the galaxy looks kind of big. So, can you use this other simulation? We've got a slightly different way of projecting the dark matter density, and right, and it looks like this. Right, so you have to just slightly change the color scheme and how intensely you color the dark matter, because of course it doesn't give light, right? So we have to invent something. And here you really see that we are not only part of this dark matter halo, but that halo is again, seems to be part of some larger network. You see these tendrils reaching out to grasp at other parts of this, perhaps some kind of cosmic web of dark matter. Okay, so can we actually see any of this cosmic web? Actually, we can if we look at very large scales. So if you look at large enough scales, you see that the galaxies, right, so just ordinary light, stars, right, it seems to follow these kind of cosmic tendrils of a cosmic web. And this pattern, this is from real data, it's from the 2DF Galaxy Survey. There have been many more accurate galaxy surveys that look much further out, like the Sloan Digital Sky Survey. There's soon going to be a very exciting one called DESI that's going to produce much more new data. But the beautiful thing about this is that it exactly matches what we have in these computer simulations. So I think the Zoom is reconnecting, but we can keep going. So that's dark matter. That's sort of the galaxies following this cosmic web of dark matter at large scales. We believe that dark matter is the backbone of this cosmic web. We'll see in a bit that this is what we think is actually, the dark matter is providing the seed for this cosmic web to appear. Okay, let me re-share my screen so the Zoom folks can continue to follow. Okay. Now, the reason I said this is sort of the biggest problem is because of the amount of dark matter that there exists. Through various means that we'll talk about in a moment, we can figure out some ratio of the dark matter to ordinary matter. And it turns out that of the matter in the universe, only 1%, 1 in 100, is stars and planets like us. And then everything else, the 99% of the rest, consists, 15% is other matter that hasn't yet or will never collapse into stars. It's mostly like thin ionized gas in between galaxies. But the rest is this, sorry, let me get back to the Zoom. I hope the Zoom gods will be favorably disposed for the rest of the evening. So there all this rest, 84% is dark matter. So it's a huge component of our universe, and you would expect that such a huge thing has many influences on many astrophysical systems, and we'll see in a bit that indeed it does. Now perhaps you've heard of something else than dark matter. You've heard of something called dark energy. So I've drawn these pyramids to scale, so this is actually 1% of this area above the line, but that's counting just the matter in our universe. If I were to count the sort of the energy in the universe, you also have to include a kind of energy of empty space. So that's not a form of matter, it's a kind of extra thing that makes the universe expand faster. But that's really a fundamentally different thing. So I'm not going to be talking about this in detail today. We're just going to be talking about different kinds of matter, things that are substance, that can be more here than there, that can be pulled around by gravity. Yeah, sure.
So if both of them are dark,
yes,
and we cannot see, how do we distinguish between matter and energy?
Yes, that's a great question. So dark matter, we have many evidence for it. I'll show you several systems in which dark matter has an impact. For dark energy, the only effect that it has, the only one, is that it slightly helps accelerate the expansion of the universe. So dark energy becomes only important at very, very large scales. When you have a lot of space, and all that space has a little bit of dark energy, and it accelerates the expansion of the universe. Whereas dark matter, not only is it important for the expansion of the universe, but it also affects galaxies and galaxy clusters and many things in the early universe.
And I guess the dark energy is uniform?
Exactly. Yeah, it is in fact just an energy of empty space. So there seems to be this strange property that if I take a meter of space, it has a tendency to produce a little bit more space. And then you have more space, right? So it's going to produce even more space later. right? So it's going to help accelerate the expansion of the universe. This was only discovered a few decades ago. Yeah. But we have an excellent model for it. The model I just told you, if you write it down in math, that is basically enough. It is not a very complex system. Whereas dark matter, there's clouds and tendrils, and it interacts with gravity, with other matter. So there's much rich physics in here. There are still also a lot of scientists studying this. Many of my colleagues do. I don't want to make it as if this is less interesting, but I do want to help you understand why I study dark matter and not everyone is studying dark energy. Yes?
So I have a quick question. All right, so we've got the dark matter and then we have the energy.
Mm-hmm.
What is outside of that?
What is outside that?
It's expanding. What is it expanding into?
Okay, so that's great. That's a great question. So the funny thing is that it's not like a big explosion, right? So it's not that the universe is expanding into more empty space. It's just that the space itself is expanding, and we have no idea how large the universe really is. Right? It could be much larger than the universe we can see. We can only see as far out as basically the universe is young. The universe is 13-point-something billions of years old, so those regions will have time to send the light to us, but how large the universe really is, we honestly don't know. That's mysterious. Maybe it's infinite, we don't know. All right.
We killed it.
We killed it.
So, no worries.
Okay, good. Sure, yeah, no worries. Click leave? Okay. We have left the Zoom. Sorry, folks.
In the dark.
All right. So I've told you how we define dark matter, where it is, how much of it there is. Now let's talk a little bit about what it could be. So there's a couple of candidates you could think of. You can of course think of unusual particles. We'll talk a lot more about that. Maybe you've heard of neutrinos, which are very weakly interacting particles, which we know exist. We can see that even in experiments on Earth. Nuclear reactors produce them. Radioactive decays produce them. So maybe if there's a lot of these neutrinos, also feebly interacting, could be dark matter. But it could also be a completely new undiscovered particle. Right? Now I'm just listing options. You'll see later that not all of these options are possible anymore. But maybe I don't need to have an unusual particle. Maybe all I need is a dark compact object. Right? It can't just be some gas, then we would have seen it. Right? There's a lot of gas and it would absorb some light or emit some light. It's made of lots of little compact dense objects. As long as they don't emit light, it could also be something. So maybe it's neutron stars, or rogue planets, or black dwarfs, or white dwarfs that have completely cooled down. And maybe it's black holes, right? You know that stars, especially the massive stars, when they die, they leave a black hole remnant. And maybe there's just a lot of these black holes. And maybe it doesn't even have to be from stars. Maybe they're from the early universe. So very early on in the universe, there was already a lot of black holes produced. Could be dark matter. So these are roughly the ideas that people have tried over the years. The current status, at least in my view, and I think the view of most of my colleagues, is this. Neutrinos are ruled out. There's no way it can be dark matter. And the universe would look very differently if neutrinos were the dark matter. For new undiscovered particles, there are many options. There are thousands of ideas. So it's important to realize when we say, scientists, that something is mysterious, that we're wondering what something is, that doesn't mean we have no idea. Rather, it's usually the opposite. We have so many ideas, and all those ideas, any one of them, can reproduce what we see. And we just need to measure more and more carefully to distinguish between all these different ideas. Other possibilities. Neutron stars and black holes from former stars are also ruled out, and we'll see why. Spoiler alert, it's going to be because dark matter is already present in the early universe. So then it can't be black holes from former stars, because they haven't had time to form any stars yet. Black holes from the early universe, though, that's still possible, but it's pretty difficult. You still need some new physics to make these black holes. So I and most of my colleagues are studying new undiscovered particles, but I'm very happy that there's also lots of people studying black holes and doing measurements on that to try and rule out these last couple of models that are still possible. It would be great if that would be the solution. We don't need any new particle, but it looks like many people believe that we do. Okay, that's part one. Do you have any questions so far?
So how do you know they're filaments or something? I mean, you can't see it. How do you know there's filaments? How do you know
that's right. right? So we can actually see filaments if we look at a larger scale. So if you look at a larger scale, we'll see in a bit that dark matter forms is sort of the seeds of the formation of galaxies. But if you have only a little clump of dark matter, you cannot attract enough gas to make a galaxy. If you have a very large clump, you have this large filament, you can form galaxies into it. So the galaxies will trace these filaments of the dark matter. But you're completely right, you can't see these filaments. We'd love to see them, but we can't. Maybe in the future, though, there is a way to see this dark matter, even though it gives no light, using only gravity. That's what I'll talk about at the end of my talk. Okay. More questions? Yes?
So when you mentioned that it could be more somewhere and like less like somewhere else, like do we know that it exists around us as well, in proximity of like here?
That's a good question. We know that there must be a lot of it in the galaxy. In every galaxy, almost every galaxy in the universe. But do we know there's a lot of dark matter right here? Or could you imagine some situation where this distribution was a little different, right? There wouldn't be this big blob of a halo, but it would be like sort of filaments all the way down. It would be all little tendrils, and we're just not hitting a tendril. Yeah, that's a possibility we can't exclude at the moment. So that is possible, but almost all the models that we work with predict some kind of very smooth distribution. But there are occasionally differences, right? So you can imagine, right, if all these, many of these halos have a galaxy embedded into them, what happens if a galaxy crashes into another galaxy? Right, then that messes everything up. Now there are like little streams of dark matter passing through each other. And we believe that there are some of those in our galaxy as well. More questions? Yes?
Just a kind of side question to his then, and this is not really a question, I guess I'm asking you to verify my understanding, that if there's dark matter in this room, it's at a scale where it's either too uniform in this room for us to notice, but you're talking about on like these galactic scales, then the differences start to become apparent. So we could be totally chock full of dark matter in this room, we just would have no way of knowing it because we're all equally saturated.
No, I think that's completely right. I would just add to that dark matter does interact through gravity. So if there would be like a huge ball of dark matter weighing thousands of kilograms, we will be able to see it with very sensitive experiments. So most models of dark matter, including the one I'm showing here, predict that there's only a tiny amount of dark matter on Earth, on the order of a gram on the entire Earth, including the center of the Earth. Right? So it's extremely small. The only reason that it dominates the matter contribution in the universe is because it is so spread out, right? If you think about it, like matter has ways of collapsing because it interacts strongly and it can cool down, it can emit light. But dark matter has much more trouble doing this, so it can't form these very compact structures like stars and galaxies. It's a good question. What exactly the distribution of dark matter is at a small scale, we would love to know, because that would tell us something about what dark matter is. Okay. Short question, or shall I move to part 2? Part 2. Okay, great. Why do we believe it exists? Well, some of this Antonio already mentioned, right? So we had our first, I would call, hints of dark matter already 100 years ago. So when people observed these kind of systems, so this is the Coma cluster that Fritz Zwicky looked at, and he could observe like what the different velocities of the galaxies were, right? You can take a spectrum of a galaxy, you can see a Doppler shift in a line, and through that you can try to infer, okay, would that match with the kind of masses that I think the galaxy have? Or you're sort of counting, thinking how many stars is there, how many lights being emitted, how much mass does it take to emit that much light? And what you get is an estimate that is totally wrong. What you would get is that if there's only the regular matter here, this cluster would fly apart. The way they would call it in astronomy is it would evaporate very quickly. So yeah, people said, okay, let's write that down. Let's solve that in the future. Now, in the early 20th century, there were lots of problems in astronomy. We had just figured out how stars worked and that galaxies were actually very far away. And, so this was a problem, but there were many problems. You can also observe other clusters. So here's the Virgo cluster, a very, very nice nearby cluster. where you can do the same kind of analysis, and you would also see that this cluster just doesn't have enough mass to keep the galaxies together. They're moving around too quickly to be held together by their own gravity. Something else must be pulling all those galaxies in. This galaxy, by the way, it's called M87. That's the one that the first black hole image was taken from. So it's actually, it looks very, very quiet here, but it has a supermassive black hole at the center that is very active and emitting lots of radiation. Okay. Right, so that was another observation that you could do. But the real, what people often remember as evidence for dark matter is this. Let me see that I hope the video will work. Always videos and PowerPoint is always a difficult thing. Let me play it for you. Here we go, play it. Almost there. Okay, well I can explain without the video as well, but it's much nicer if you see the galaxies actually rotating. So this relates to the work of Aalbers that Antonio also mentioned. So if you look at how galaxies rotate, what you will see is that especially the outskirts of the galaxy are rotating quite quickly. Now it's very similar to the clusters. If you see something that's moving very fast and it's not just flying away, there must be something pulling it in. And the only thing that can do that here is gravity. So if you see the outskirts of the galaxy rotating very fast, you see that in our neighboring galaxy and in another galaxy and another galaxy, it looks like there's some extra matter here that isn't just accounted for by the stars. So again, that was another hint that we could write down, like, hey, maybe there's something else going on here. There's some new kind of dark matter. Interestingly enough, even after seeing these things, many people were not yet convinced about dark matter. There were still many open problems to solve. They thought, yeah, maybe there could just be a lot of extra gas that we haven't found, or some other dark thing. Why would we need new physics to explain this? Maybe the laws of physics are actually a little bit different on very large scales. There's lots of possibilities for this. That all changed a few decades later, when we get the rise of physical cosmology, when we start looking not just at individual galaxies, but at the universe as a whole. So let me give the basic picture. Just to mention that the idea of finding, can I restart the slideshow again? So the idea of finding new things by their gravity. Oh, now it's rotating. Great. Okay, here you can see. Right, so this is how people would have expected the galaxy to rotate if it was just its own mass, right? So you see the center is rotating quickly, but over here things are rotating much more slowly. If you rotate quicker, you would fly away. Whereas for what you actually observe is much more like this. So you see that. Yes?
Could you explain how we estimate the speed of rotation of galaxies?
Sure. So for that you need to estimate the speed of stars. And so for that you need to accurately determine the position and ideally also the velocity of stars. So especially the velocity going towards and away from us, you can measure with what's called spectroscopy. So you can look at the light emitted by a star, and there are certain lines in there that correspond to particular processes in physics happening there. Now, if the star is moving towards you or away from you, the light is slightly redshifted or blue shifted, just like a Doppler effect. Just when you hear an ambulance coming towards you, moving away from you, the frequency changes. So with that, you can determine that velocity going towards you. And at least for stars nearby, you can also estimate the motion on the sky. If you just look back, if you look at the star again a while later, basically, you may see small or proper motions. You need to do that very accurately. It's not as easy as determining the motion towards you or away from you, but that is a way to do it. And then you measure it for a lot of stars, and you make a big computer model where you take them all together, and then you get an estimate of the velocity of the stars.
Does this mean that if I was like a science educator or something, and I was trying to show the different speeds of different galaxies in like a picture, like one of those telescope pictures, because I know that the telescope pictures are heavily computer adjusted so that it's visible, pretty looking colors to humans as opposed to, infrared stuff and whatnot.
Yeah.
So does that mean that if I apply the right kind of transformation across the color values, I could theoretically have all my galaxies be half blue, half red to
Absolutely.
different degrees. Like I could intentionally emphasize that the approaching side is more blue and the retreating side is more red.
No, you're completely right. That's in fact one of the ways that we often determine for far away galaxies what's happening. We can't resolve individual stars if the galaxy is far away enough. So we use a technique, it's called integral field spectroscopy. What it really means is that you're just doing this thing that you did for a particular star, but now on a large part of your image. So you're seeing on a part of the image, hey, here things are more red, and here things are more blue. You literally get the pictures you described. Yeah, that's a way to measure galaxy rotations. Okay. But I want to tell you about what really convinced people that this dark matter thing is something we have to reckon with, and that is cosmology, right? So because the idea of finding new masses by seeing unexplained motions in other masses is very old, right? Does anybody know what this is?
The sun?
Any guesses? Okay, so it could be Venus, right? It's a very hard one because it just looked like a white ball. Lots of things look like a white ball. So it is a planet. I can tell you that. It's not Venus. Which one do you think it is? Uranus, exactly. So this is Uranus. And when you look at the orbits of Uranus very closely, you see that there's kind of perturbations, that is not really following the expected laws. They knew about this, and some clever astronomers started calculating, and eventually sent I was about to say an email, but I guess they sent a carrier pigeon or something to people operating the telescopes to say, hey, could you look over there? I think there's something there. You know what they found? They found some matter, right? Neptune, exactly. They found this guy, Neptune. That's how you discover Neptune, right? You look at Uranus, you see the orbit's a little weird, you find Neptune. So this is not an unusual idea to astronomers. The unusual bit comes when you look at the entire universe. So we know now that the universe started off looking very differently from it does today. The universe is not some kind of steady state. It had a very hot and very dense beginning. So there was a rapid expansion at the beginning. We can see sort of the afterglow of that expansion when the universe just became transparent to light. And then slowly galaxies congealed together, actually around the dark matter filaments, but we'll get to that. And they slowly congealed together to form the universe that exists today. So that opens up a lot of new things we can study about the universe, because suddenly we can look very far away when the universe was in a very different state. And we can try to explain how did it get from there to here. So there's a couple of things you can look at. So if you look at normal matter, what's happening today is if you take a clump of normal matter and it starts to collapse under gravity, what will happen is that it will radiate away some of its energy, right? If you collapse, you gain energy, right? You're falling into something. And if you want to keep falling, you want to form something, you better get rid of that energy, otherwise you'll just pass straight through. So the way stars solve that is by radiating away some energy. And before nuclear fusion even starts, already some energy is being radiated away. In the early universe, you can't do that. Because to radiate away energy, the universe got to be cold. If the universe around you is as hot as you are, then, you know, good luck getting rid of that energy, right? So what happens if you have a clump of matter in the early universe and you push on it, it pushes back. You can't form these kind of stars and structures yet. Instead, what you get is a kind of balance. That if you have a little bit of extra matter, then it starts to collapse under gravity and bounces back. And it starts to kind of oscillate. So you kind of get an oscillatory motion that you could look for in this early universe data. Dark matter is completely different, right? It can't make stars because it can't radiate away that energy when it collapses. But in the early universe, it could start to collapse a little bit. Because if you, it doesn't have this problem that it pushes back, right? It doesn't interact strongly with itself. So it can start to collapse and form this sort of cosmic tendril-like web. So now we've got a lot of different things we can look at to try and see what matter is the universe actually made of. There's roughly two things you look at. The first is this, it's the afterglow of the Big Bang. There's something in front of this, that's our galaxy. So we first got to get rid of that using some good analysis techniques. Or you can just look at a little patch over here where it's not a problem, but you can get rid of it as well by observing basically in many different frequencies. And you get this beautiful pattern, the afterglow of the Big Bang. It's also called the cosmic microwave background, or CMB. What I'm showing you here is very, very small regions where it's a little bit hotter or a little bit colder. And if you analyze this pattern in detail, what you're going to see is exactly these kind of oscillatory motions that I was talking about. So you see that this matter actually underwent these kind of oscillations. And the mathematics of that are slightly complicated, and I will not bore you with, but basically you're decomposing this whole pattern into waves of different sizes. So you've got one wave that spans the entire sky, one wave that goes up and down twice, one 4, one 8 times, etc. And then you measure how much is that little harmonic going up and down. If you do that very accurately, that's these black little dots. They're actually not dots, they're what we call error bars. So they're just a measurement where we say, oh, it's somewhere in between these things. The measurement is so precise that the error bar is almost invisible. And then you see if it matches. So here we have this model called lambda CDM. That's our current best model of the universe. That's what I showed you the data for, like mostly dark matter, among the matter, but also some dark energy and normal matter. Fits like a charm. Beautifully described. So you can measure all these points and it fits beautifully. You try something else, no dark matter, no luck. No luck at all. You can't even get near the measurements. You try something more complicated, like there's a very complicated new theories of physics, where you have new forces happening, essentially modified gravity. You can get close for a little bit. Seems to work all right. Whoops. Now you're in trouble. So it is very difficult to measure, to match these higher order peaks. Can you do it by making the theory complicated enough? Absolutely. No problem. You just add enough terms and corrections and eventually you'll get there. But by then your theory has become a little less attractive, right? Yeah, exactly, epicycles. Yes, question?
So scientists actually ruled in the fact that maybe the entire rules of physics is actually wrong, and they tried to predict it based on that as well, and it didn't work, but dark matter did.
Yeah, so what the people here did was that they tried a modification to the laws of physics that was suggested by these galaxies that were rotating faster, basically saying that gravity is a little weaker at small scales. And they also took on board some of Einstein's insights, which work really well when gravity is very strong, and tried to combine those into a consistent theory, and then adjust the knobs until it fits this model. And that works very well for the beginning, but it does not work towards the end. And I would just make the point that if you make the model even more complicated, eventually you'll get it to match, but by then, no, it's very difficult. Okay. So that's very nice evidence, but we got another one, an even bigger one, where you don't even need to do a very complicated analysis to appreciate it. And that is called structure formation. So remember this picture that I showed, all these galaxies forming these little tendrils. Well, we can reproduce that in a computer simulation. So I start the universe off with normal matter and dark matter, and I just let it evolve. And what I see is that I can reproduce these tendrils. You can quantify this again with some nice methods. You'll see good agreement. But the more important point is that to get any kind of structure like this at all, you need dark matter. Right? Remember this picture that I drew in the beginning. In the early universe, matter cannot cluster together. Right? If you try it, it will push back. But dark matter can. So if you try to run one of these computer simulations without dark matter, what happens? Nothing. You get not even a single galaxy. The matter is just sort of homogeneously distributed, and yeah, it's not exactly equal everywhere, but the universe expands and nothing ever happens. So without dark matter, we wouldn't be here. Without dark matter, there wouldn't be galaxies and stars in the sky. Without dark matter, the sky would be dark, and there would be no one to see it. So that's why dark matter is a problem, right? So we can measure this quantitatively as well, right? So you can look at the amount of structure, so how clumpy is the universe on different scales. You can look at really large scales where the universe looks very smooth. You get this cosmic microwave background. Or you can look very close, like at galaxies and at anything in between, clusters of galaxies, superclusters. And everywhere you look, it's beautifully fitted by these computer simulations that include dark matter. In fact, until recently, when people wanted to simulate the universe, they didn't bother to include the matter. Dark matter is such a big influence on this, you can just only do dark matter simulations. And then later on, you can sort of put the matter back in, because it's a small effect. And that doesn't really work if you want to get the very small structure right, because when you're the size of a galaxy, matter definitely matters, right? And you don't get these beautiful disks of spinning stars otherwise. But for all of this, dark matter simulations work beautifully. Okay.
Back
Yeah,
to
yeah.
the previous one.
Mhm.
So at the solar system scale,
Mhm.
you said like 1 gram for the.
That's sort of for the Earth. For the solar system, it'll be a little bit more.
How can you even detect anything like that? Or is it
Solar system scale, very difficult. Yeah. So you would need a kind of dark matter model that we briefly talked about, where dark matter is actually very dense in some places and not in others. So like big black holes, then you could try to detect it on the solar system scale. Otherwise, tough luck. Yeah, not through its gravity at least. Yeah. But maybe dark matter interacts a little bit with, for example, the sun. Right? Maybe it interacts a little bit with particles and accumulates in the center of the sun, and you could look at the center of the sun, at least the particles that are emitted from it, you might see something. So there's various ways you can try, but basically this is something for larger scales, galaxy-sized or above. Okay. There's a couple other pieces. Some of you have seen this image. Yeah, do you remember it? Right, the president was sitting in front of it at some point. Right, this is from the James Webb Telescope, showing a beautiful gravitational lensing cluster. So what that means is, you see lots of these normal white blobs here in front. Those are just galaxies. And then you see all these weird, like blobs that are sort of, these amoebas that are morphing around in the image. And this is actually very similar, that if you hold a wine glass up to a lamp, you will also see a dent in these kind of weird shapes. So this is lensing, but not by glass, by space-time itself, by gravity. So it is the gravity that is bending the light of these very distant galaxies, they're all the way red, into these weird shapes. And you can predict how much of this lensing should happen based on the mass of these galaxies. And once again, you come up way short. You need to add lots of dark matter in order to explain these kind of lensing features. Just another nice thing that you can see it. So here you can really see how these, you really get all these weird shapes of galaxies. You can analyze this quantitatively. It's very beautiful, but it's already striking just by itself. But this lensing effect has an extra kicker in some situations. What if you have two clusters of galaxies that just crashed into each other? So that's what's shown here. This is called the bullet cluster. So here we have actually, you see a lot of galaxies again in front. The blue and the red, those are actually not colors, so they're from a different data set added back in later. The red shows a hot gas, shown with detected with an X-ray telescope. It's so hot it emits X-rays. And then the blue is the reconstructed distribution of mass from gravitational lensing. Because you can again see some of these little arcs over here, and from that you can infer where should most of the mass be. So what you're seeing here, these clusters just crashed into each other. Well, what happened? Well, most of the mass is in this gas, and that sort of, that crashed into each other. It experiences some shocks and some friction, so that's where most of the ordinary matter is. But if you look at the mass itself, so from gravitational lensing, that just passed right through each other. So here you can see a separation happening between the ordinary matter and the dark matter. So this, people, when it happened, they claimed this, now finally we have direct evidence for the existence of dark matter. I would still like to detect it in my detector in a lab, but it is a very beautiful demonstration of how dark matter, even in these extreme systems, you can see it, and sometimes you get even a glimpse of its nature, it being dark. Right. Right. So this is just the picture that I had earlier of like the early universe versus today. That matter in the early universe gets its oscillatory behavior. Today it makes stars. Dark matter does not do that. It enters into a kind of equilibrium where, unless there's some big collision, it just sits around. It does move around, but you cannot easily separate it from the ordinary matter this way. And in the early universe, it has a super important role of seeding this cosmic web, providing the seeds of the first little bit of structures that started accreting gas and forming galaxies. So to summarize this part, the best evidence we have for dark matter comes from cosmology. Right? It seeds the growth of galaxies. We would not exist without it. It precisely matches also the cosmic microwave background and structure formation data. So we know that 300,000 years, that's the time of this background afterglow, dark matter was already there and was already dark. Because otherwise you cannot explain this particular afterglow pattern. So that's what ruled out some of these models where you say, oh yeah, it can't be like rogue planets or something, because those aren't there in the early universe. almost every large astrophysical system, by large I mean galaxy-sized or above, shows evidence for dark matter. So you're talking rotation of galaxies, Lubin, velocities of galaxies and clusters, Zwicky, and many other scientists that work on these fields. Gravitational lensing, colliding galaxy clusters, you name it. Whenever something is galaxy-sized or large, you bet dark matter has a big influence on it. That's why we believe dark matter exists. Okay.
So when you say almost everyone, are there ones, is there anything which you would think should show evidence for dark matter that doesn't?
Let's see, so there are some galaxies that don't appear to have dark matter. And what we basically think, that in a sense that is evidence for dark matter. Because if it was instead some modification of the laws of physics, then every galaxy should show it. And if one galaxy doesn't, then there's something missing. And what's happening is probably, it's always hard for if you see a few observations, something like this. If you have a big collision, you can separate the matter from the dark matter. So if something like here in this gas starts to form another galaxy, then the dark matter is just gone the other way. So then that's one way you might end up with a galaxy without a lot of dark matter. But to your question of are there people who still work on alternatives to dark matter? Absolutely, and I want to stimulate that. That's great. We should keep working on, can you come up with a simple physical theory that explains all of these features? Usually, if you come up with a theory, it explains one of those features, and you have to even work at it for that. Not so much for rotation of galaxies, that can be explained with a quite simple modification of physics. If you're going to explain the cosmic microwave background or structure formation, that's a tall order. And so that's why most people think that dark matter is the simplest model to explain all of these observations at once. But I'd love to see a simple physical theory that can do it as well. That would be amazing. More questions?
This rotation of galaxies you show us, like two galaxies, is it all of them are rotating on the right side, or some of them are rotating like on the left and some on the right?
Now I'd have to speculate, but I would guess that they're rotating in different sizes. There's no particular preference like you have on Earth when you're forming a depression, like a weather system. You have the Coriolis force, right? That the Earth is rotating. But there's no such thing in the universe. So my guess would be that equal amount of galaxies rotate one way and the other way.
No. I mean at the speed, at this speed, like the outside edge of the galaxy rotates fast and slow. So, like on the right side, it was rotating fast.
Yeah.
So, and the left side, so it's like simulation or like
this is absolutely a simulation.
Like observed galaxies. Do they rotate as shown on the right?
Yes.
Profile of velocities, or
Yep.
profile of velocity. Some of them is on the left.
No. So that's what I was talking about. Is there are some galaxies that don't appear to have dark matter, but they're extremely rare. Like almost all galaxies have the pattern of velocities that are shown on the right. And there's variations, because the galaxies is a whole zoo of variations. There are galaxies that just collided, galaxies that have not had any collisions for billions of years and that have stopped forming stars, and so there's definitely variation. But basically every galaxy we know is in a dark matter halo. And we can see its effects through its rotation curve. Yes?
What instruments do you, or methodology do you use to study all of this? I mean, do you have like a telescope time, or do you have like a set of data, or lots of sets of data that you analyze from like different sources? Like, how do you come up with all of these? What's your matter?
That's a great question. So the data I've shown you is collected, going all the way back to the 1900s. But nowadays also with modern telescopes. So if you want to study the early universe, or the cosmic microwave background, let's see if we can get there. Now we seem to be stuck at these rotating galaxies. First they didn't want to rotate. But if you want to study this, you need to observe at a different wavelength of light. So basically this is microwave light, so similar to the radiation that's used at heat up your cup of tea. And to see this, you can do it from Earth, and there are certainly telescopes that do that, but this particular one was taken from space with the Planck satellite, and before that there was the WMAP satellite and the COBE satellite, and usually these measurements have now been replicated several times. If you want to study gravitational lensing, this kind of stuff, you need a very sensitive space telescope. So this is the James Webb Space Telescope. This was one of the first images that it took. If you want to study the galaxies at large scales, then you need to take a very big survey of the entire sky. And there are many telescopes, usually on the ground, that do that. So, for example, the upcoming Vera-Rubin Observatory, named after Vera-Rubin, is going to map out many galaxies. This is the 2DF survey. There's the Sloan Digital Sky Survey. There are many of these telescopes. Many telescopes, many wavelengths that we use to observe different parts of the universe. Okay. Yes?
When you see gravitational lensing and you see the arcs, is the redshift of that light preserved in the process, so you can tell how far the hidden galaxy is?
Exactly. You can find out what kind of path the light took. Right. So in fact, if you look at these lensing images, you can see the answer to your question. Right. These things are red, right? Mm-hmm. And they're pretty early galaxies. In fact, if there were no redshift, I would have expected them to look blue, because if I just started making lots of stars, you still have all the massive stars, and they're a little bit bluer than the stars that get very old. So definitely, redshift is still happening. The redshift is happening because space is expanding, and this from very far away. So that's why the redshift is there. Yeah. So this is actually an important technique and can be used to figure out how far away are these galaxies, how's the expansion of space exactly working.
And if you have a whole series of arcs like that, if you look at the spectra of the arcs, you can tell whether it's a single source or whether there's more than one galaxy.
Yeah, exactly. Sometimes you can get, certainly in these strong systems, that one galaxy has multiple images, right? Just like the light bending around it. Let's see, go ahead.
Is there also any influences in the subatomic scales? Like, is there a model that is it a model that helps understanding something that you don't know in small scales as well?
Beautiful question. That's what we're working on right now. And that's what I'm going to try to talk about in part 3. But to give a very quick spoiler, yes, there are many dark matter models motivated by problems in subatomic physics that have a dark matter model, and that's one of the reasons it's popular. But there's a couple of problems we'd like to solve, and there's different possible dark matter candidates that you can invoke. Can I propose I move to part 3 and we take more questions at the end? Okay. Right. Part 3. How do we detect dark matter? Right, so what I'm talking about now is getting a detection of ideally a single dark matter particle in the lab with a detector. So that's not looking at the gravity of like very large dark matter systems. That'd be the ideal case. But I'd settle for a gravitational observation as long as it gives me a detailed model for what the dark matter is. Like what kind of particle is it made of? Or if it's not a particle, what kind of black holes or whatever it is. There's roughly speaking 4 techniques. So I call them here high energy and low energy based on what kind of observations you need to do. So in the lab at high energy, we can try to make dark matter. So we can try to smash 2 particles together at a huge speed. And when you have lots of energy, you can make lots of particles, right? It's basically E is mc squared in action. So this is one of the detectors at the Large Hadron Collider in CERN, where they see lots of interesting things. They discovered a new particle called the Higgs boson in the 2010s. And they're also looking for dark matter candidates. How would you see them? Because dark matter would just vanish, right? It would just not be visible. Well, you see it because if you add up the energy and momentum of the speed of all the particles you do see, then you're going to see there's something missing, right? You add up all the energies and you're like, hey, where did that go? That would be evidence for dark matter. People did a lot of studies, haven't found anything so far. Spoiler alert, that's going to be the story of the rest of the evening, guys. I'm sorry to disappoint you, but if we had found this already, it'd be a very different talk. You can also do high energy study in the cosmos. I mentioned that maybe dark matter has a very small interaction with light or with other matter or with itself. And especially if dark matter was made early in the universe, then you might expect that it can be destroyed as well. If you have a large concentration of dark matter together, you might expect that dark matter finds maybe a dark antiparticle that's living around there and annihilates into a burst of light, like a gamma ray, or a burst of something else which eventually decays into a gamma ray. So people have done that too. It's called the Fermi satellite. It has looked for gamma ray emission in the entire sky. Of course, you find something because there are many interesting astrophysical processes that can make it. There's a couple places, like in the center of the galaxy, where there seems to be an excess of these gamma rays being produced. And that excess could be consistent with dark matter destroying itself, basically. Only problem here is that there's other explanations for that excess, which basically involve very rapidly rotating neutron stars, which we know must exist also in this wild region in the galactic center. So there's interesting hints here, but people have looked at it for a long time, but there's no convincing proof as yet that this constitutes evidence for dark matter. But there is a lot of intriguing data out there. So what can you unearth? What can you do at low energy? So now you're not trying to make or destroy the dark matter, you're just trying to detect its influence. So what we can do on Earth, and this is something that I worked on, is you can try to detect dark matter scattering of ordinary particles. So maybe dark matter doesn't do that. Right? Maybe it only interacts gravitationally. That would be very unfortunate. But if it does, then we should be able to see it. So you make a detector where you can detect very rare light flashes of dark matter scattering with ordinary matter. And I'll tell you how these detectors work in a second. And finally, there are some gravitational probes that I might have some chance to mention at the end, where you basically look and try to find these very small tendrils of dark matter that are around the galaxy and try to discover its signature. And can that maybe tell you something about what dark matter is? Right, so let's focus on this for the moment. Let's try to find a rare scattering of dark matter. And so here's just the three non-gravitational probes together in a kind of diagram particle physics physicists often like to draw. So here you have two particles coming together doing something that we're not going to talk about and producing dark matter. So that's what we're doing, colliders. You have the opposite process of dark matter destroying itself and then detecting ordinary particles. We're going to do this. So we're going to get an ordinary particle just to sit here, and we're just going to wait till the dark matter particle comes around and gives it a bit of a jolt. That's all we're going to do. So, okay, I want to build a dark matter detector. What have I got to bring? Well, I got to be able to see the effect of those dark matter scatters. So if I actually get a bump from dark matter, I want to make that visible. So what happens if you give atoms or things a kick? Well, you might get an emission of light. You might get an emission of charge, right? So you give an atom a big kick, there's all these electrons around the nucleus, and some of them get left behind or kicked off. Or you might get some heat, right? There's a bit of motion, and it eventually gets transmitted into other atoms because more chaotic, and it is a form of heat. You can try to detect all three. Okay, that's making the scatters visible, but I only want to catch a lot of them. So how do you catch a lot of fish? Well, you need a very big net. Right? So you need a lot of atoms, basically. You need to get a very massive detector. And it turns out in quantum mechanics that it really helps also to have a very big nucleus. The details are a little hard to explain, but what's basically happening is that a particle is also behaving like a wave and scattering a bit of all of the different nucleons in the nucleus at the same time, and it's enhancing the effect. Doesn't really matter, just get a lot of nuclei, that'll also do you very good. And finally, I don't want to see anything else. Right? When I see a light flash, I want to know that was dark matter. So there better not be radioactivity around. Right? And there's a lot of radioactivity in the world, so I need to really minimize that. There's like thousands of radioactive decays happening around us, even in our bodies. So we need to do special materials. And we need to go deep underground to be shielded from cosmic rays that are bombarding us from outer space. So the way we do that is with something called liquid xenon detectors. There are many other ways of doing this. I'm going to tell you the one that I work on, and I think it's also one of the best ones. That's why I work on it. So we set some of the most stringent constraints on dark matter. So liquid xenon, so xenon's a noble gas. You probably know helium. Xenon is sort of a heavier cousin of helium. So the beauty of that is that it can certainly transmit charge, right? And noble gases, if you remember your chemistry, they don't do a lot of chemistry. So yeah, you probably don't cover them a lot in chemistry. There's not much to talk about. So if you just dangle an electron by a xenon atom, it doesn't care. It has all the electrons it needs. Whereas many other atoms, like hydrogen atoms, extra electron, great. And then you lost the electron. For light, there's a very special property that xenon has. Most materials emit and absorb light at particular frequencies, so what you would get is, sure, you emit some light, but then the next atom absorbs it, and then emits it, and absorbs it, and it can take very long to get out, and you will never see anything definitive. But xenon has a very funny property that after you kick an electron out, or you excite an electron, it can do a chemical trick where it forms two xenon atoms together into a molecule, just like a hydrogen molecule is two hydrogen atoms together. That molecule is unstable, it will decay very quickly, but when it does, it emits light that the other xenon atoms that are not molecules can't absorb. Okay. So there's a chemical trick that allows noble gases like xenon to transmit light. Liquid xenon, you get a lot of it. That's kind of becoming a problem for us because xenon's a little expensive. It's more expensive than silver. So that's a bit of a problem. You can go to other noble gases like argon, but they have other problems. And it is, of course, a very big nucleus, like more than 100-something nucleons in the xenon nucleus. We use very low radioactivity. Xenon has no important radioactivity in itself, and we go very deep underground to be shielded from cosmic rays. So the detector looks something like this. This is schematically. So here's the little tank of liquid xenon. So a dark matter particle is hopefully going to come in and give the xenon atom a little bit of a kick. When it does, it will bump around the other atoms and excite them and cause a little light flash. And we can detect it with light sensors that are placed on top and on the bottom of the detector. So that gives this little light flash. But it also liberates some electrons. You remember, this noble gas doesn't care about the electrons. So we apply a little electric field, right? So a bit of positive charge over here, and we just lure the electrons to come up. They come into gaseous xenon, which is floating on top. And there, we can accelerate those electrons, because gases are much thinner than liquids. So we can, with a bit of electric field, accelerate them. They bump into more xenon atoms. You get lots more light. That gives you a nice second signal. So you get two signals, and they help you figure out where in the detector this happened. Right? If the electrons take a very long time to drift, these signals are far apart, whereas if the dark matter particle hit over here, it would be closer together.
What's the temperature of the liquid xenon?
It's it's around the temperature of liquid nitrogen. The exact number is, I would have to.
I just wondered.
Yeah, so you can cool it with liquid nitrogen if you want. Yeah. Right, so that's how the detector roughly works. Dark matter bumps into it, you see light, you see charge. And also the balance between these two signals can help you differentiate a dark matter signal bumping into the nucleus from like a gamma ray knocking an electron off. You get a slightly different signal. Okay, let me skip this. Let me just show you how these detectors look. So let me give you a little virtual lab tour. So we're gonna drive out. We're gonna fly into Rome to beautiful Italy and drive out to the Gran Sasso Mountains. And you get to this beautiful facility over here. And there's a little road that leads off into the mountains. There's a big tunnel, and inside that tunnel, if you're halfway through the mountain, you go left. So you're still inside the mountain, and you go left. And they dug out a beautiful hole for you. And inside that hole, you see something like this. So we built a very big tank over here. And here's a little building with all kinds of wires and devices to keep the xenon cool, to store the xenon if something goes wrong. And that's the xenon 1-ton detector that I worked on before. With my colleagues in Stanford, I'm now working on a different detector called Lux Zeppelin. I'll show you a few pictures of, but most of the pictures are for this one. So the actual action is happening inside the tank. You see this little poster we put on top, because we can't have the tank open, that'd be a bit of a problem. That's what's happening inside. But I can take you inside, no problem, right? This is what you see if you go inside. The whole thing is filled with water. And that water is there to protect us against the cosmic rays that still make it all the way through the mountain. Occasionally that still happens. When they do, they leave a track in this water that we can detect. So,
how many meters underneath the earth?
Order a kilometer, so a little bit more than a kilometer. So it's a big mountain.
1 kilometer?
Yeah. So to get close to the detector, we're first going to have to drain the water. Let me drain the water for you. And then you see something like this. So not only was there water in it, we put reflective foil all around the edges, so that if there is a signal from these cosmic rays, it will be detected by some little light sensors. I'm trying to find, yeah, you see a light sensor, you see some light sensor. But this isn't our detector. This is just the outer detector. These kind of detectors are made out of they're little onions. And every time you peel off a layer, you get to a cleaner and a more sensitive detector. So if we really want to see the detector, we got to go inside this metal vessel called a cryostat, which is meant to cool things. So we're going to screw the bottom cap off. We're going to place a clean room around it, because we need to keep it very, very clean, of course, otherwise contaminants get in, and see what the detector looks from the inside. It looks something like this. Right, so I've taken this metal thing off, And now you see that there's all these copper rings over there. So they're for keeping this electric field stable, that we're guiding these electrons all the way to the top. And here on the bottom you can see all these light sensors that detect very small little light flashes. And they're connected to all these wires that reach out to this building where the physicist can sit and receive the data. What's inside the cylinder? Okay, let me screw off this bottom cap and let's look inside. Normally there's liquid xenon in there, it wouldn't be very healthy. So we've removed the liquid xenon, and you can see something like this. So I've now also removed some of these bottom light sensors, and you can look into the heart of our detector. You can see the top light sensors over there. And if you look carefully, you can also see some little wires. Right? Those are also those are the electrodes that help us generate this electric field. That if there's some electrons being generated, they'll be pulled to the other side of the liquid xenon, where they will generate extra signals. So that's the xenon 1 tunnel detector. You don't have to go to Italy. You can also go a little bit closer. You can go to South Dakota. There is a hole in the ground, and there used to be a gold mine over here. They got a lot of gold out of this, and at some point it ran dry. And then some physicists came to them and said, "Hey, can we use your mine? It's pretty deep in the ground. Not this particular hole, but there's another shaft going deep in the ground." And that's the Stanford underground research facility where there is the Lux Zeppelin detector, which is just basically a larger version of the detector you just saw. So you don't have to go underground, you can also go deep underground. Okay, here's just the light sensor arrays before the LZ was assembled. Okay, we haven't found dark matter. We have found a few other things. We found some very rare nuclear decays. So at one point we reached a nice cover, then we can go to our funding agency to say, yeah, we are doing useful things. We found a nuclear decay, so there's a radioactive decay with a half-life of, let me see if I get this correctly, 1,000,000 quadrillion years. So if you got absolutely
like observed galaxies, do they rotate as shown on the right?
Yes.
Profile of velocities, or
yeah.
Profile of velocities, some of them is on the left.
No, so that's what I was talking about. Is there are some galaxies that don't appear to have dark matter, but they're extremely rare. Like almost all galaxies have the pattern of velocities that are shown on the right. And there's variations because they're galaxies. There's a whole zoo of variations. There are galaxies that just collided, galaxies that have not had any collisions for millions of years and that have stopped forming stars. And so there's definitely variation. But basically, every galaxy we know is in the dark matter halo. And we can see its effects through its rotation. Questions? Yes. In the 1900s, but nowadays also with modern telescopes. So if you want to study the early universe, so the cosmic microwave background, there. Now we seem to be stuck with these rotating galaxies. But if you want to study this, you need to observe at a different wavelength. So basically, this is microwave light, similar to the radiation that's used at cup of tea. And to see this, you can do it from Earth, and there are certainly telescopes that do that. But this particular one was taken from space with the Planck satellite, and before that there was a WMAP satellite, a COBE satellite, and usually these measurements have now been replicated several times. If you want to study gravitational lensing, this kind of stuff, you need a very sensitive space telescope. So this is the James Webb Space Telescope. This was one of the first images that it took. If you want to study the galaxies at large scales, then you need to take a very big survey of the entire sky. And there are many telescopes, usually on the ground, that do that. So, for example, the Colin Vera-Rubin Observatory, named after Vera-Rubin, is going to map out many galaxies. This is the 2EF survey. There's the Sloan Digital Sky Survey. There are many of these telescopes. Many telescopes, many wavelengths that we use to observe different parts of the universe. Okay. Yes?
When you see gravitational lensing and you see the arcs, is the redshift of that light preserved in the process so you can tell how far the hidden galaxy is?
Exactly. You can find out what kind of path the light took. Right. So in fact, if you look at these lensing images, you can see the answer to your question, right? These things are red, right? And they're pretty early galaxies. In fact, if I if there were no redshift, I would have expected them to look blue, because if I just started making lots of stars, you still have all the massive stars, and they're a little bit bluer than the stars that get very late. So definitely, redshift is still happening. And redshift is happening because space is expanding, and it's from very far away, so that's why redshift is there. Yeah. So this is actually an important technique and can be used to figure out how far away are these galaxies, how's the expansion of space exactly work.
And if you have a whole series of arcs like that, if you look at the spectra of the arcs, you can tell whether it's a single source or whether there's more than one galaxy.
Yeah, yeah, exactly. Sometimes you can get, certainly in these strong systems, that one galaxy has multiple images, right? Just like the light pattern. Let's see, yeah, go ahead.
Is there also any evidences in the subatomic scales? Like, is there a model that is it a model that helps understanding something that we don't know in small scales as well?
Beautiful question. That's what we're working on right now. That's what I'm going to try to talk about in part 3. But to give a very quick spoiler, yes, there are many dark matter models motivated by problems in subatomic physics that have a dark matter model, and that's one of the reasons it's popular. But there's a couple of problems we'd like to solve, and there's different possible dark matter candidates that you can invoke. Can I propose I move to part 3 and we take more questions at the end? Okay. Right. Part 3. How do we detect dark matter? Right, so what I'm talking about now is getting the detection of ideally a single. You also need to consult with experts in the xenon market and how you get it. You want benefit? When you don't experiment, you can sell it again. So it's not that it's being used. Yeah.
So in this experiment with xenon detector, you were testing if these particles have other interaction than gravitation.
Yeah, exactly.
Right. So because you say maybe the gravitation will be ignored. But then I think what about estimates, like you say, on our Earth we may have 2 grams, right?
Yeah.
So then you can calculate how many particles, and then you can estimate what's the radius of the particle. And then maybe this radius is, I don't know, smaller of electron or whatever, and then you calculate the probability. Maybe you didn't wait long enough to...
Yeah, no, that is certainly possible for some of the more massive dark matter particles, right? If dark matter has itself a mass of a gram, then there's like 1 passing through the Earth at any given moment. So yeah, then it's going to be very difficult. But most models for dark matter have masses that are more on the order of the mass of a proton. So here you see roughly a spectrum of dark matter mass that are likely. So if you have the mass roughly of a proton, then there's like 10 to the 23 or something particles in grams. So there's quite a lot of particles out there, and you've got a good chance of seeing it. And we've been able to put very stringent constraints on the interaction between dark matter and ordinary matter this way. And you can only do that if there's a lot of dark matter particles passing through your regular. But you're right, that is a calculation you need to do. And when you get to the very heavy dark matter particles, then there can't be that many of them, because you know how much mass there is in the dark matter. So if dark matter is very heavy, there's very few of them, that becomes a problem.
Okay, so currently you wait long enough, right?
Yes, yeah, at least we wait for many years. And the reason we stop at some point is actually not because we need to wait for dark matter to come in, but because there are other signals that are confused with dark matter that at some point they just build up. So there's still occasionally a bit of radioactivity coming in. So then, yeah, your measurement basically, you see all this radioactivity, and it's very, very much more difficult to see a tiny bundle of extra signal on top of it. So if we had a completely background-free detector, we should wait for like 100 years. But we stop in practice after like 5 or 10. And then we build a bigger one and do it again.
Any other questions? If not, let's go more.
Let's do more.
So the experiment you mentioned in CERN, does it just proves that dark matter cannot be made with the real matter, like the matter that we actually see, or?
So they haven't seen dark matter at CERN. So that means that you can't make it by smashing protons together at a particular speed. So they measure at a certain energy they smash it together, and that's not enough to make dark matter. But it could be, if you just accelerate it faster, you could make dark matter. So maybe the dark matter is actually one of these heavier guys, so you need a lot more energy to create them. So in that case, you could make them at CERN. Or maybe it's just very hard to make the dark matter in that kind of experiment. You need to not mash protons together with electrons together, or do something else. So yeah, there are other ways you can try to make dark matter. And there are some dark matter modes that we will never be able to see at CERN, and others where we just need to upgrade the detector to see more of it. By doing the experiments, we learn about dark matter because we include the models that would have predicted signals. Any questions?
I do have a question, but I'm embarrassed by it because I'm worried it'll get.
No worries, please.
Why do we assume that gravity is an attractive force as opposed to assuming that the expansion of the universe is the default sort of thing, and that when two masses attract each other, it's because those masses are just really good at consolidating the distance between each other. And this would, something like that, if you're kind of assuming it, like imagining this like a ticker tape sort of situation, right? Then I would have just assumed that dark matter isn't a matter, but just kind of leftover computational space from where matter used to be.
Okay. So that starts getting into like some theories of holography, maybe, or black holes. But you're talking about new theories of physics that maybe explain the sort of the odd features that you see here. There's already a lot of room in our existing theories of physics for interesting stuff. Like gravity is not always an attractive force. It can be a repulsive force if you've got strange enough energy. Dark energy is an example of this. Dark energy is something that causes the universe to expand, and it can be modeled as a kind of repulsive gravity. That may have also occurred in our early universe. Dark matter, though, it definitely seems to be something that attracts, right? It is in all its behaviors consistent with basically any normal substance. But it just doesn't interact.
Yeah, I think of my dad who used to explain gravitational lensing to me. He told me to imagine like a piece of cloth, like a t-shirt material, like kind of stretchy, right? Kind of elastic. And you put a marble in it, and it stretches it stretches near the marble, and that's what creates this like pit. And if you roll something toward the marble, it'll get stuck in the gravitational element. And so, if you're thinking of space like that, but you don't assume that it's elastic, if you assume that it just deforms each time, then couldn't dark matter just be kind of like, like when the wagons were crossing the prairies, they would get these wagon wheel struts, like these ruts, where because so many things had passed over that one spot before, eventually it became a permanent stuckness. And you could think of that as like being an attractive force of a type. So if dark matter is just leftover space from things that used to be there, then other things would also get stuck there, and they would just kind of constantly be reinforcing.
So thanks for sharing that theory. That could be a very interesting thing. We should perhaps talk about it afterward to get more details.
That's why I was embarrassed about
let me just say that any modification of the laws of physics that you would do, that's essentially what you're proposing. Right? You're proposing a different way that space-time curves in response to matter. They would have to answer not just to the data I showed you. Pick out the right one. So we should talk afterwards about your idea. But keep in mind that all ideas need to be tested with data. So we're trying to.
Okay. So I just want to say, those of you, did you have a question?
Yeah, good. Have there been any anomalies found in the orbits of the Pioneer or Viking, not Viking, but the Pioneer voyages? As they had very long distances from the Earth, they discovered some clutters on the solar system size.
Yeah, that's a good question. I'm not an expert on the detailed treatment of them, but I know that those are being studied. And occasionally, indeed, when somebody comes up with a new theory of physics, they refer to such anomalies and try to explain them. And other scientists say, oh, there's a simpler explanation, and it's debated. But yeah, I'm not an expert on the specific anomalies.
So I want to say, you'll sit for a few more minutes after I say. So first of all, thank you again. Personally, I hope to have you sooner so you can report on the results. So thank you.